Hello, friend, and welcome back to Night Whisper Science. I am Neil Tyson, and tonight I will be your guide for our continuing series, Whispers from the Milky Way. Settle in now. Find that perfect place of comfort and stillness. Allow the weight of your body to sink deeply into the surface beneath you. Let go of the day. Release its thoughts, its cares, its hurried pace. Here, in the quiet of the night, we travel with our minds, journeying to the farthest reaches of understanding. Tonight, we are going on a search for something that cannot be found with our eyes. We are venturing into the vast, silent, invisible universe, the realm of dark matter. It is a journey that requires not sight, but imagination, not speed, but stillness. As you breathe in, imagine you are drawing in the calm, cool darkness of interstellar space. And as you breathe out, feel any remaining tension dissolving away, like a distant star fading from view. The universe is filled with wonders that announce themselves with brilliant, blazing light, incandescent stars, swirling nebulae, entire galaxies that glitter like jewels on black velvet. But the deepest secrets, the most profound truths, are often whispered in the silence, hidden in the dark. Tonight, we will learn to listen to that silence. We will learn to feel the presence of the unseen fabric of reality. So relax your mind, quiet your thoughts, and join me as we drift into the cosmic shadows to explore the beautiful, deep, and tranquil mystery of the 20 hidden facts about dark matter. The first thing to understand as you begin to drift and float on the gentle currents of your own breath is that the universe you see, the one that has captivated humanity for millennia, is only a tiny fraction of what is actually there. All the stars you can see with the naked eye, all the galaxies ever photographed by our most powerful telescopes, all the planets, moons, asteroids, and shimmering clouds of gas, all of it, together, makes up only about 5% of the total mass and energy of the cosmos. The rest is a profound and beautiful mystery. About 27% of the universe is something we have come to call dark matter. So, for every cupful of matter that makes you, your bed, the air you are breathing, and the distant stars, there are more than 5 cupfuls of this other, different substance. It is the invisible architect of the cosmos. Imagine you are in a vast and ancient cathedral in the dead of night. It is so dark you cannot see the walls, the ceiling, or the great stone pillars that hold the roof aloft. But you know they are there. You can feel their presence. You can sense the shape of the space around you. You walk forward, and your path is guided by invisible structures. You reach out your hand, and though you see nothing, you might feel the cool, solid surface of a column that was there all along, silently shaping the room. This is what it is like to live in our universe. We are living inside a grand cosmic cathedral built by an invisible architect. Dark matter is the unseen scaffolding, the silent framework upon which everything we know and see is built. So why do we call it dark? The name is perhaps a little misleading. It isn't dark in the way that a lump of coal is dark or a black cloth is dark. Those things are dark because they absorb the light that hits them. Dark matter does not. It isn't dark like the empty space between stars, which is dark simply because there is nothing there for light to come from. Dark matter is profoundly, fundamentally different. It is dark because it has no relationship with light whatsoever. Light, the electromagnetic force, is the messenger of the visible universe. It's how we see, how we feel warmth from the sun, how our radios and phones communicate. Dark matter feels none of this. A beam of light from the most powerful laser could be aimed at a great clump of dark matter, and that beam would pass straight through it as if nothing was there at all. It does not emit light. It does not absorb light. It does not reflect or scatter light. It is utterly, perfectly transparent, a ghost in the cosmic machine. And so we cannot see it. We cannot point our telescopes at the sky and take a picture of it. And yet, we know it is there. We can feel its presence, just as you could feel the pillars in that dark cathedral. We feel its gravity. Gravity is the one language dark matter speaks that our universe can understand. Its immense mass pulls and tugs on the things we can see, and in its gentle, persistent gravitational embrace, the entire visible cosmos takes its shape. It is the silent partner in the great cosmic dance, leading the brilliant shining stars and galaxies in a waltz across billions of years. As you settle deeper now into a state of serene relaxation, imagine this invisible substance all around you, passing through the walls of your room, through the very ground beneath you, and through your own body. A gentle, ceaseless river of particles that you will never see and never feel flowing through everything. It asks for nothing, it disturbs nothing, it simply is. The quiet, invisible majority, providing the stable foundation for all the beauty and light we cherish. It is the universe's greatest secret, hiding in plain sight, everywhere, all at once. It is the invisible architect. And how did we first come to suspect this architect's existence? How did we first learn of this great invisible presence? The story begins with the quiet, meticulous work of an astronomer named Vera Rubin. In the 1960s and 70s, she was doing what many astronomers do, patiently watching the stars. She was studying the way galaxies spin. Imagine a spinning carousel or a merry-go-round in a playground at night, with each horse lit by a single small light. From a distance, you can track the speed of each horse by watching its light. The horses near the center move in small, quick circles. The horses on the very outer edge have to travel a much greater distance to complete a rotation, so you would expect them to move more slowly. If they moved too fast, the chain holding them would snap, and they would fly off into the darkness. This is simple physics. It is a fundamental law dictated by gravity. In a galaxy, the vast majority of the visible matter, the stars, the gas, the dust, is concentrated in the bright central bulge. So, just like with the carousel, astronomers expected that the stars on the outer edges of a galaxy, far from the central mass, would be moving much more slowly. They should be moving at a leisurely, relaxed pace. If they moved too quickly, the gentle pull of gravity from the visible matter in the galaxy wouldn't be strong enough to hold them in their orbits, and they should simply fly off, cast away into the lonely void of intergalactic space. But that is not what Vera Rubin found. Night after night, pointing her telescope at the Andromeda galaxy and others, she measured the speeds of these outer stars. And she discovered something astonishing, something that seemed to defy the laws of physics. The stars on the outer edges were moving just as fast as the stars closer in. They were moving far, far too quickly. The carousel was spinning at a reckless, impossible speed, yet none of the horses were flying off. They were all holding on, held in place by some tremendous unseen force. There simply was not enough visible matter in the galaxy to account for the gravity needed to keep these speeding stars in their orbits. It was as if an invisible hand was holding the entire galaxy together. A cosmic glue, preventing it from tearing itself apart. That glue, she and her colleagues proposed, was a vast spherical halo of invisible matter, extending far beyond the visible, glittering disk of the galaxy. A substance whose gravitational pull was directing the show, keeping every star in its place. This was the first powerful, undeniable evidence for dark matter. It was a revolutionary, challenging idea, but the evidence was written in the starlight. The universe was not what it seemed. Vera Rubin's work revealed that the beautiful, swirling spirals of galaxies we see are like the white foam on the crest of a deep, invisible ocean wave. The foam is what we see, what captures our attention, but the true power, the immense substance, lies in the unseen water beneath. Dark matter is that cosmic ocean. It is the galactic glue. And as you continue to relax, to drift, feel the gentle, reassuring strength of that invisible hold. The same force that keeps the stars of the Milky Way from flying apart is the same fundamental force of gravity that holds you softly to your bed. It is a persistent, calming presence, a quiet, firm grip that holds our entire cosmic home together in its cosmic dance. a slow, silent, gravitational waltz that has played on uninterrupted for billions of years. Now, let us zoom out, pulling our awareness away from a single galaxy and its stars and looking at the grandest scales of the cosmos. If dark matter is the scaffolding for a single galaxy, what does the scaffolding of the entire universe look like? For decades, astronomers mapped the locations of thousands upon thousands of galaxies. And as the maps grew more complete, a stunning picture began to emerge. The galaxies were not scattered randomly through space, like seeds thrown to the wind. Instead, they were arranged in a breathtakingly complex and beautiful pattern. They formed long, delicate chains and filaments stretching for hundreds of millions of light years. These filaments connected at dense, busy intersections, great hubs of galaxies we call clusters. And in between these filaments were vast, dark, empty regions known as voids where very few galaxies reside. It looked like a network, a colossal three-dimensional web filling all of space. The question was, why? Why would the universe organize itself in such an intricate way? The answer, once again, lies in the silent, gravitational work of dark matter. Computer simulations, some of the most complex calculations ever undertaken by humanity, have allowed us to recreate the evolution of the universe from its earliest moments. In these simulations, we see that in the primordial soup after the Big Bang, tiny fluctuations in the density of dark matter began to grow. Gravity is a patient, relentless force. Where there was slightly more dark matter, gravity pulled in more, and where there was less, it became emptier. Over millions and then billions of years, these initial seeds grew into the vast structure we see today. The dark matter formed a cosmic web. Imagine a spider's web on a cool, still morning covered in dew. The web itself is nearly invisible, a delicate, translucent structure. But the glistening droplets of water have collected along its threads, and at the junctions where threads meet, revealing the web's hidden pattern. In this metaphor, the nearly invisible web is the dark matter, and the shining droplets of dew are the galaxies. The normal matter that we are made of, the hydrogen and helium gas of the early universe, was pulled by gravity into the densest parts of this dark matter web. It flowed along the invisible filaments like rivers, pooling in the great gravitational wells at the intersections. And in those deep pools, the gas became dense enough to collapse, to ignite, and to form the very first stars and galaxies. So when we look out into the night sky and see the faint, distant light of other galaxies, we are seeing the luminous decorations on a hidden, grander structure. We are seeing the dew on the spider's web. The galaxies exist where they do because the dark matter told them where to go. It is a structure of unimaginable scale and delicate beauty, a filigree of invisible matter upon which all the light of the cosmos is strung. As your mind drifts now, picture this cosmic web. Feel yourself a part of this vast, interconnected structure. The filamentary pathways of dark matter are the cosmic highways, and the galaxy clusters are the great, sparkling cities. It is a reminder that nothing in the universe is truly isolated. Everything is connected, part of a silent, invisible network that stretches from one end of the cosmos to the other. And you are here, now, resting peacefully at one tiny, luminous point within that magnificent cosmic web. It is natural, then, to wonder, what is this substance? If it is not the familiar matter of our world, then what can it be? Early on, astronomers considered more mundane explanations. Perhaps they thought dark matter is just normal matter that is, for some reason, very difficult to see. Maybe it's made of things like faint, dead stars called white dwarfs, or neutron stars, or even black holes, all drifting silently through the halos of galaxies. This type of matter, the stuff of protons and neutrons that makes up you and me and everything we know, is called baryonic matter by physicists. So the search was on for massive, compact halo objects, or machos. Astronomers watched millions of stars, looking for moments when a macho might pass in front of a star from our perspective. The macho's gravity would act like a lens, momentarily causing the distant star to brighten. And while they did find some of these events, they found nowhere near enough to account for the immense amount of dark matter that Vera Rubin's observations required. The universe was simply not filled with enough dead stars or dim objects. Perhaps, others suggested, it was vast clouds of cold hydrogen gas, invisible to most telescopes. But these clouds, were they to exist in such quantities, would absorb light at specific wavelengths, leaving a telltale fingerprint on the light from distant quasars. And when we looked, that fingerprint wasn't there. One by one, every candidate made of normal baryonic matter was ruled out. The conclusion became inescapable. Dark matter is not just dark. It is different. It is something new, something exotic. It must be made of a particle or particles that lie outside of our current, beautiful, and incredibly successful theory of particle physics, known as the Standard Model. The Standard Model describes the 17 fundamental particles that build our world: electrons, quarks, photons, the Higgs boson. It is a triumph of science. But dark matter doesn't seem to fit. It is a ghost that haunts this otherwise perfect house of physics. Imagine you have a key that can unlock every single door in your house. It fits the front door, the bedroom doors, even the small lock on your diary. You begin to believe you have the master key to everything. Then one day, you discover a new door in your house, a door you've never seen before. And your key doesn't fit. It doesn't even go in the lock. This is the feeling that dark matter gives to physicists. It suggests there is another realm of reality, another layer to the universe, with its own particles and perhaps even its own forces that we have only just begun to glimpse. This isn't a failure of our science, it is an invitation. It is the universe, in its quiet, mysterious way, telling us that there is more to learn. There is another door to be opened. So as you rest here, let go of the familiar. Allow your mind to embrace the truly unknown. The universe is not just stranger than we imagine, it is stranger than we can imagine. And this mysterious substance, this non-baryonic matter, is a gentle, cosmic reminder of that beautiful, humbling truth. If dark matter is made of some new, exotic particle, a particle beyond our standard model, what might it be like? Over the years, theoretical physicists, the great dreamers and mathematicians of science, have imagined many possibilities. But two leading candidates have emerged from the elegant equations of cosmology and particle physics. They are known as WIMPs and axions. Let's begin with the WIMP. The name stands for Weakly Interacting Massive Particle. Massive because whatever it is, it must have mass. It is its mass and its gravity that holds the galaxies together. Weakly interacting refers to the way it might communicate with our world. In physics, the weak nuclear force is one of the 4 fundamental forces responsible for certain types of radioactive decay. The idea is that WIMPs might only feel gravity and this weak force. They are impervious to the powerful electromagnetic force, which is why they are dark, and to the strong nuclear force, which holds the centers of atoms together. Because their only interaction with us is so incredibly weak, they would behave like ghosts. Right now, at this very moment, scientists calculate that hundreds of thousands, perhaps millions, of these WIMP particles are streaming through your body every single second. They pass through the floor, through the entire planet Earth, and out the other side, almost never touching a single atom. They are a silent, invisible river in which we are all constantly bathed. The other leading candidate is a particle called the axion. It is a very different kind of ghost. The axion was first proposed not to explain dark matter, but to solve a completely different problem in particle physics. It was a theoretical quirk, a loose thread in the mathematics of the strong nuclear force. But physicists soon realized that if this particle existed, it would have the perfect properties to be dark matter. Axions would be incredibly lightweight, far, far lighter than electrons. but they would have been produced in such immense astronomical numbers in the very first moments of the Big Bang that their combined mass could easily account for all the dark matter we see today. If WIMPs are like individual ghostly cannonballs, axions are more like a vast, coherent, invisible wave flowing through the universe. Imagine a still, quiet pond. A WIMP passing through is like a tiny, invisible pebble dropping in, creating almost no disturbance. A sea of axions, however, would be like a slow, gentle, imperceptible current flowing through the entire pond itself. Both of these candidates, the WIMP and the axion, are compelling. They arise naturally from our deepest theories about the universe, but as of now, they remain phantoms, theoretical ghosts waiting to be discovered. The search for them is one of the greatest quests in modern science. It pushes the boundaries of our technology and our imagination, and it reminds us that the universe is populated by more things than we have yet dreamed of. As you lie here on the edge of sleep, feel the gentle, harmless passage of these theoretical particles. Feel yourself as part of this invisible cosmic river. It is a flow of pure mystery, a current of unanswered questions, carrying you softly now towards a state of deep and peaceful rest. So, if we cannot see dark matter with our eyes or touch it with our hands, how can we be so sure it's there? How can we map its location on the cosmic web? We do it by watching the one thing dark matter cannot hide from: light. Not its own light, but the light from other, more distant objects as it travels across the universe to reach our telescopes. The secret is revealed by one of Einstein's most profound predictions. His theory of general relativity tells us that massive objects do not just pull on other things. They literally bend and warp the fabric of space-time around them, and light, as it travels through space, must follow these curves. This phenomenon is called gravitational lensing. Imagine a candle burning on the far side of a room. Now, imagine placing a heavy, distorted piece of glass, like the bottom of a wine bottle, between you and the candle. As you look through the glass, the image of the candle flame is warped. It might be magnified, stretched into an arc, or even appear in multiple places at once. The glass has bent the path of the light rays coming from the flame. In the cosmos, a massive object, like a galaxy cluster, acts as that piece of glass. And a great clump of dark matter, which is far more massive than the visible galaxy cluster, acts as an even more powerful, though completely invisible, lens. So, when we look out at very distant galaxies, which are like the candles, their light has to travel for billions of years to reach us. On its long journey, that light might pass through or near a massive cluster of galaxies, and, more importantly, through the vast halo of dark matter surrounding that cluster. The immense gravity of that dark matter bends space-time, and the light from the distant galaxy follows that bend. When the light finally reaches our telescopes, it is distorted. We might see the distant galaxy stretched into a long, thin arc of light. We might see multiple images of the same galaxy scattered around the invisible lens. By studying the precise shape and pattern of these distortions, astronomers can work backwards. They can calculate exactly how much mass must be present in the intervening lens and precisely where that mass is located. It is like reconstructing the shape of the invisible glass by looking only at the distorted image of the candle flame. And time and again, these calculations show us that the vast majority of the mass doing the lensing is invisible. Gravitational lensing allows us to create a map of the dark matter. It allows us to see the invisible. It is a stunning confirmation of Einstein's theory and one of the most powerful pieces of evidence for the existence of dark matter. It turns the entire universe into a giant observatory, using cosmic gravity itself as the telescope. So, as you relax even further, picture the silent, patient journey of a single photon of light. Born in a distant star, it travels across the empty eons in a perfectly straight line for billions of years. Then, as it nears our own cosmic neighborhood, its path is gently, gracefully bent by an invisible sea of mass. Its journey is diverted, guided by the unseen architect before it finally ends its long voyage in one of our telescopes, bringing with it a secret message, a warped whisper that tells of the invisible structures that command the cosmos. Perhaps the most dramatic and beautiful example of this cosmic lensing, the clearest evidence that dark matter is real and distinct from normal matter, comes from an object known to astronomers as the Bullet Cluster. It isn't a single object, but rather the result of a titanic and violent collision between two entire clusters of galaxies. The event took place over 100 million years, a cosmic ballet on a scale that is almost impossible to comprehend. Imagine two great swarms of fireflies flying towards each other in the night. The fireflies are the individual galaxies. As the two swarms pass through each other, the individual fireflies, being small points of light with vast spaces between them, will mostly just fly past each other, their paths bent by gravity but without actually colliding. This is what happened to the galaxies in the Bullet Cluster. They passed through each other like ghosts. However, each galaxy cluster is not just made of galaxies. It also contains a vast cloud of hot gas spread out between the galaxies. This gas, which is normal baryonic matter, is far more extensive than the galaxies themselves. It is like two enormous clouds of smoke in which the fireflies are embedded. When these two giant clouds of gas collided, they crashed into each other with tremendous force. They slammed together, creating a massive shockwave, heating up even more and slowing down dramatically, just as two smoke clouds would merge and stop. So now the scene is set. The galaxies have passed through each other and are on the other side of the collision. The hot gas, the normal matter, has collided in the middle and been left behind. The critical question is, what happened to the dark matter? If dark matter were just another form of normal matter, it would have stayed with the gas, slowed down in the middle. If it were some modification of gravity, there would be no separation at all. But that is not what we see. By using the technique of gravitational lensing, by observing how the light from even more distant galaxies is bent, astronomers were able to map the location of the mass in the Bullet Cluster. And what they found was breathtaking. The map showed two distinct clumps of mass. And these clumps were not in the center, where the hot gas was. The clumps of mass had passed right through the collision, just like the galaxies. They were on the other side of the crash, having barely slowed down at all. The dark matter, being weakly interacting, did not notice the collision. It felt only gravity. It behaved like two invisible cannonballs passing straight through two colliding clouds of smoke.
This observation is often called the smoking gun evidence for dark matter. We can clearly see the baryonic matter, the gas, in one place, and the gravitational effect of the bulk of the mass in a completely different place. It is a direct observation of dark matter separating from normal matter, a photograph of the ghost leaving the machine. As you sink into a state of profound calm, visualize this cosmic event, the silent, effortless passage of the invisible substance through the chaotic, fiery crash of the visible. It is a testament to its gentle, non-interactive nature, a quiet, powerful demonstration that our universe is composed of at least two very different kinds of reality, interpenetrating each other, living side by side, but obeying very different rules. One crashes and burns, the other simply passes on through. The story of the cosmos is not just written in fire and light, but also in temperature and speed. The way the universe is built, the reason we have these beautiful, grand structures like the Milky Way, depends critically on the character of dark matter in the earliest moments of time. Specifically, it depends on whether it was hot or cold. Hot dark matter would be made of particles that were moving at tremendous speeds, close to the speed of light in the early universe. Imagine trying to build a sandcastle with dry, wind-blown sand. The individual grains move so fast and so randomly that they cannot clump together. Any small pile you make is immediately blown apart. A universe filled with hot dark matter would be like this. Its fast-moving particles would zip around, smoothing out any small density fluctuations, erasing the tiny primordial seeds of structure before gravity had a chance to nurture them. In such a universe, the very largest structures, like superclusters of galaxies, would form first, and smaller things like individual galaxies would have to form later by fragmenting from these enormous clouds. But this is the opposite of what our telescopes tell us. Our observations show that small things formed first. Small clumps of dark matter created the first small galaxies, which then merged and grew over billions of years into the larger galaxies and clusters we see today. This points to a different solution. The leading theory, the one that so beautifully matches our observations, is called cold dark matter. Cold in this context doesn't refer to temperature in the way we usually think of it. It simply means the particles were moving slowly in the early universe. They were sluggish, placid, and unhurried. Imagine trying to build your sandcastle now, but with thick, wet, heavy sand. It clumps together easily. Every small pile you make stays put, and you can add more and more, building it up into a grand structure. This is what cold dark matter did. Because its particles were moving slowly, gravity could easily grab hold of them. The tiny, denser regions of dark matter in the early universe grew steadily, pulling in more and more of their slow-moving brethren. They were the patient, gravitational seeds. They formed the first small dark matter halos, the invisible nurseries where the first galaxies would be born. The slowness of dark matter was its creative secret. Its patient, deliberate gathering over eons allowed for the bottom-up construction of the entire cosmic web. So, as you feel your own body slowing down, your breath becoming deeper and more regular, connect with this idea of cosmic stillness. The universe is not just a product of explosive energy. It is a product of deep, patient, and productive calm. The slow, cold beginning of dark matter was the quiet foundation upon which all the subsequent light and life was built. Science is a journey of discovery, and sometimes the most exciting discoveries are the ones that don't seem to fit. They are the beautiful puzzles, the exceptions to the rule that challenge our understanding and point the way to a deeper truth. For decades, the story of dark matter seemed universal. Every galaxy we studied seemed to be held together by this invisible glue embedded in a massive dark matter halo. It was the cosmic rule. Then, in 2018, astronomers studying a faint, diffuse-looking galaxy called NGC 1052-2 found something that seemed impossible. They measured the motion of the star clusters within it, expecting to find the telltale signature of dark matter's gravitational grip. But it wasn't there. The stars were moving slowly, exactly as you would expect if the only gravity present was from the stars themselves. This galaxy appeared to have almost no dark matter at all. It was a ghost of a galaxy, made only of visible matter. This discovery sent a wave of excitement and gentle confusion through the astronomical community. If dark matter is the essential cosmic scaffold, the invisible seed from which every galaxy grows, how could this one exist without it?
It's like finding a great old tree in the middle of a forest, standing tall and proud, but with no roots. It seems to defy the very nature of what a tree is. Since that initial discovery, a few more of these dark matter-deficient galaxies have been found, and they are profoundly important. Paradoxically, a galaxy with no dark matter is one of the strongest pieces of evidence that dark matter is a real substance. It proves that dark matter is not just a misunderstanding of gravity. If gravity were simply different on galactic scales, as some alternative theories suggest, then every galaxy should feel that modified gravity. But the existence of galaxies like DF2 shows that the visible matter and the dark matter can be separated. You can have the tree with its roots, and you can, apparently, have the tree without them. How these galaxies formed is now a beautiful new mystery. Perhaps they were formed by a high-speed collision between two gas-rich galaxies, where the gas, which forms stars, was stripped away from its dark matter halo. Or perhaps they represent a completely new, unknown pathway for galaxy formation. We don't yet know. But as you drift and dream, hold this gentle puzzle in your mind. The universe is not a simple, monolithic place. It is filled with complexity, with exceptions, with beautiful anomalies that invite our curiosity. The lonely galaxy with no dark matter is not a problem for the theory. It is a clue, a whisper from the cosmos, telling us that the story is even more rich and fascinating than we ever imagined. For every rule, there is an exception.
And for every exception, there is often its polar opposite. Just as there are galaxies with surprisingly little dark matter, there are others that are almost nothing but. In 2016, astronomers turned their telescopes towards a large, faint, and almost transparent-looking galaxy known as Dragonfly 44. It is what's known as an ultra-diffuse galaxy. It is as large as our own Milky Way, a vast, sprawling collection of stars, but it has only about 1% of the number of stars. The stars are spread out so thinly that if you were inside it, you might not even realize you are in a galaxy at all. It is a celestial puffball, a cosmic dandelion seed. But when astronomers measured the speed of the few star clusters they could see within it, they found another shock. The clusters were moving incredibly fast, far faster than could be explained by the sparse population of stars. For Dragonfly 44 to hold itself together, for it not to have simply dissipated into the void, it must be held by an immense amount of gravity. The calculations were astonishing. They showed that the galaxy must be composed of 99.99% dark matter. It is, for all intents and purposes, a dark galaxy. The few shining stars we see are just a faint, glittering sprinkle on top of a colossal, invisible structure. It is the complete inverse of NG 1352-DF2. It is a tree that is almost entirely made of roots, with only a few tiny leaves to show for it. Imagine a vast, invisible cloud the size of a city, and suspended within that invisible cloud are just a few tiny, sparkling motes of dust. That is Dragonfly 44. It gives us a sense of what the universe is truly like. The substance is the invisible. The light is just a minor decoration. These dark-dominated galaxies challenge us to rethink what a galaxy even is. They are laboratories for studying the nature of dark matter in its purest form, where its gravitational effects are not confused by the complex physics of stars and gas. They are the quiet giants of the cosmos, hiding in plain sight. As your awareness begins to diffuse, becoming as soft and gentle as the light from these galaxies, allow yourself to feel this sense of emptiness and substance all at once. The feeling of being in a realm that is mostly invisible, mostly unknown. It is a peaceful, humbling thought. We are the sparkling dust motes suspended in a vast, invisible, and deeply mysterious cosmic cloud. The quest to understand dark matter is not confined to looking up at the sky. It is also a journey deep, deep down into the earth. If dark matter particles, like the ghostly WIMPs, are truly all around us, constantly streaming through the planet, then very, very rarely, one of them might just interact with normal matter. The odds are astronomically low, perhaps one interaction per year in a huge mass of material. To have any hope of detecting such a faint and fleeting event, scientists must build detectors of incredible sensitivity. But there is a problem. We live on a planet that is constantly being bombarded by a storm of other particles from space, known as cosmic rays. This cosmic radiation would create a constant noise in any detector, a blizzard of signals that would completely drown out the tiny whisper-faint signal of a single dark matter particle. So, how do you escape this cosmic storm? You go underground. You use the Earth itself as a shield.
Scientists have built some of the quietest, most sensitive experiments in the world in the deepest places on Earth. They are housed in active mines and in tunnels carved into the hearts of mountains. There is the Sanford Underground Research Facility in an old gold mine in South Dakota, nearly a mile deep. There is the Gran Sasso National Laboratory in Italy, nestled beneath the highest peaks of the Apennine Mountains. To get there, you drive through a long highway tunnel, and halfway through, a set of giant steel doors opens up, leading you into a vast, cathedral-like cavern filled with extraordinary machines. Down in these deep, silent laboratories, shielded by kilometers of solid rock from the cosmic noise above, scientists wait and listen. One of the leading types of experiments uses a huge, pristine vat filled with a rare, heavy element, like liquid xenon. The vat is lined with incredibly sensitive light detectors. The theory is that if a WIMP from the cosmic river of dark matter happens to pass through the tank and, against all odds,
bumps directly into the nucleus of a xenon atom, that nucleus will recoil, like one billiard ball hitting another. This tiny recoil would produce a minuscule flash of light and a few free electrons. And the hypersensitive detectors are there in the absolute darkness and silence, just waiting to catch that single telltale flash. It is a search that requires immense patience. It is the act of listening for a single pin drop in a hurricane, but by going deep underground, you have calmed the storm to a near-perfect silence, and now you are just waiting, listening for that one tiny ping. As you sink now into your own state of deep, quiet solitude, imagine the feeling of being in one of these subterranean labs. Feel the immense, gentle pressure of the earth above you, shielding you, protecting you. Hear the sound of absolute silence. It is a place of profound peace and profound hope, a silent, patient vigil waiting for a whisper from the invisible universe. While some scientists listen for the whisper of a direct collision deep underground, others look to the heavens for a different kind of signal, a flash of light from a cosmic crime scene. This method is called indirect detection. The idea is that if dark matter is made of particles, it must also have an antiparticle, just like normal matter does. An electron has its positron, a proton has its antiproton. If a dark matter particle were to collide with its own antiparticle, they would annihilate each other in a burst of energy, producing a shower of familiar particles and radiation that we can detect, like high-energy gamma rays. Now, such annihilations would be incredibly rare, but there are places in the universe where dark matter is thought to be extremely dense, where the chances of these collisions would be much higher. The prime locations are the centers of galaxies, like our own Milky Way, or the hearts of smaller, denser satellite galaxies that orbit our own. Here, the gravity is strong, and over billions of years, it has likely concentrated dark matter into a dense central spike. So, we point our most powerful gamma-ray telescopes, like the Fermi Gamma Ray Space Telescope orbiting high above the Earth, at these targets. We patiently scan the sky, counting every single gamma-ray photon. We know that many other cosmic phenomena produce gamma rays, like spinning pulsars and exploding stars. But the theory predicts that the gamma rays from dark matter annihilation would have a very specific energy signature. So, scientists search for an excess of gamma rays, a signal above the known background with just the right characteristics. It is like listening to a grand orchestra and trying to hear the faint, pure note of a single hidden flute. For years, there has been a tantalizing, mysterious excess of gamma rays observed coming from the center of our galaxy. It matches some of the predictions for dark matter annihilation remarkably well, but it could also be the product of thousands of undiscovered pulsars or some other more conventional cosmic process. The jury is still out. The signal is both exciting and frustratingly ambiguous. As you relax, as your mind quiets, visualize this process. Picture two invisible things drifting silently through the dense heart of the galaxy for millions of years. Then, for a fleeting instant, they meet, and in their mutual destruction, they create a tiny, brief spark of high-energy light, a single cosmic firefly in the vast darkness. That spark then travels for 25,000 years across the galaxy to finally be caught by one of our orbiting telescopes. It is another form of patient, hopeful searching, looking not for the particle itself, but for the faint, lingering echo of its disappearance. As we delve deeper into the mystery, the ideas become ever more grand and imaginative. So far, we have mostly spoken of dark matter as a single, simple particle, a lone ghost in the cosmic machine. But what if it isn't so simple? What if the universe is even more complex and beautiful than that? This leads to the fascinating speculative idea of a dark sector. Perhaps dark matter isn't just one particle. Perhaps it is an entire family of particles, a whole hidden ecosystem, just as rich and complex as our own. Our familiar world is governed by a set of forces. We have gravity, electromagnetism, light, and the strong and weak nuclear forces.
These forces allow the particles of the Standard Model, the quarks, electrons, and so on, to interact, to combine, to form atoms, molecules, stars, and people. The dark sector theory suggests that dark matter might have its own set of particles and its own set of dark forces. There could be dark photons, a kind of dark light that only dark matter particles can see. There could be dark electrons and dark protons, forming dark atoms. There could be a whole dark chemistry, a whole periodic table of dark elements. This would be a shadow universe, a mirror world, existing all around us, interpenetrating our own reality, but almost completely unaware of us, just as we are of it. The only force they would share with us is gravity. Gravity is the bridge, the one portal between these two sectors. Imagine walking through a bustling city. You see the people, the cars, the buildings. Now imagine that in the exact same physical space, there exists another, invisible city. It has its own citizens, its own traffic, its own rules. Its citizens walk right through you, and you through them, neither ever noticing the other. Their world is made of dark matter and held together by dark forces. Yours is made of normal matter. This is the grand, mind-bending possibility of the dark sector. It would mean that the 5% of the universe we can see is not just outnumbered, but that it might have a silent, invisible twin. This idea, while still highly speculative, is a powerful reminder of how little we may truly know. It opens up the possibility that the universe is not just filled with one mystery, but potentially with an entire hidden reality with its own complexity, its own beauty, and its own secrets. Let your mind gently hold this thought without needing to grasp it fully. The sense of a parallel world, not far away in another dimension, but right here, right now, sharing your space. It is a profoundly peaceful and humbling concept, expanding the cosmos, not just outwards, but inwards, into the very fabric of the space you inhabit. Let us bring this immense cosmic mystery all the way back home, to the ground right beneath you, to the planet we all share. Is there dark matter here, inside the Earth? The answer is almost certainly yes. As the Earth orbits the Sun, and the Sun orbits the center of the Milky Way, our planet is constantly plowing through the vast, invisible halo of dark matter that envelops our galaxy. A steady wind of dark matter particles is always flowing through us and through our world. Now, most of these particles pass straight through without a trace. But every so often, a dark matter particle might interact weakly with an atom inside the Earth and lose a little bit of its energy. Not enough to be detected in an experiment, but just enough so that it no longer has the speed to escape the Earth's gravity. It becomes gravitationally captured. Over the Earth's 4.5 billion year history, a significant number of these dark matter particles could have been captured in this way. Pulled by gravity, they would sink towards the densest part of our planet, its fiery, metallic core. Over eons, a small but dense ball of dark matter could have accumulated right in the center of the Earth. What would happen then? If dark matter particles can annihilate with each other, as we discussed earlier, then this dense concentration in the core would be a prime location for such annihilations to occur. Each annihilation would release a small burst of energy, a tiny puff of heat. Some theories suggest that this process, the slow, steady hum of annihilating cosmic particles deep within the Earth's core, could be contributing a small, almost undetectable amount of heat to our planet's internal engine. The warmth of our planet is overwhelmingly due to the decay of radioactive elements and the leftover heat from its formation. But it is a fascinating and beautiful thought that a tiny fraction of that warmth, a secret fire, might be coming from this hidden cosmic source. Feel the warmth and stability of the Earth beneath you. Feel its solid, reassuring presence. And imagine, deep in its center, a secret heart, where the visible world and the invisible world meet. Where particles that have traveled across the galaxy for billions of years finally come to rest, and in their final moments release a whisper of warmth that radiates up through the rock and magma to the very ground you are resting on. It is a profound connection, a reminder that we are not separate from this cosmic mystery. We are living inside of it, and it is living inside of us. In the quiet pursuit of understanding, it is the duty of a good scientist to question everything, to explore every path, even those that lead in different directions. And so, when faced with a mystery as profound as dark matter, it is natural to ask, what if we are wrong? What if there is no invisible substance? What if, instead, our understanding of gravity itself is incomplete? This is the central idea behind a compelling and elegant alternative theory known as MOND, which stands for Modified Newtonian Dynamics. First proposed in the 1980s, MOND suggests that there is no dark matter particle. Instead, it posits that Newton's law of gravity, the beautiful equation that describes everything from a falling apple to the orbit of the moon, needs a tiny adjustment when gravitational forces become extremely weak, such as on the vast, lonely outskirts of a galaxy. The theory says that in these regions, gravity's pull doesn't fade away as quickly as we expect. It has a little extra strength, a little extra reach. This modification is precisely calibrated to explain why the outer stars and galaxies spin so fast without flying away. It removes the need for an invisible halo of matter, explaining the phenomenon with a subtle change to a fundamental law of nature. For many years, MOND was remarkably successful at explaining the rotation of a wide variety of galaxies, often even more accurately than the early dark matter models. It is a beautiful idea, a testament to the power of creative, critical thinking. However, as our view of the cosmos has expanded, MOND has struggled to keep pace. While it works well for individual galaxies, it has great difficulty explaining the behavior of larger structures, like clusters of galaxies. And most critically, it cannot explain the stark separation of mass that we see in the bullet cluster. In the MOND picture, gravity is tied to the visible matter. So, the gravitational lensing effect, the bending of light, should be centered on the hot gas in the middle of that cosmic collision. But we see, with our own eyes, that the lensing is centered on the two clumps that passed straight through. The gravity is not where the normal matter is. This is the observation that MOND finds almost impossible to explain without adding its own new, complex fields that begin to look a lot like dark matter itself. Science is a process of weighing evidence, of holding two beautiful ideas in your hands and seeing which one feels heavier, which one is supported by the full weight of observation. One idea is an invisible substance, a new particle that fills the universe. The other is an invisible change to a timeless law. Both are profound, both are beautiful. But as the evidence has accumulated, from the largest cosmic structures to the afterglow of the Big Bang, the idea of dark matter has proven to be the more robust, the more encompassing explanation. And so, we continue our journey, holding MOND in our minds as a gentle reminder to always question, to always wonder, but following the path that the evidence has so far eliminated for us, the path that leads back to that mysterious, invisible substance. Let us now explore another path, another intriguing possibility for the identity of this cosmic ghost. What if dark matter is not some new, exotic, undiscovered particle? What if it is made of something we already know exists, something predicted by our theories of gravity long ago? What if dark matter is made of black holes? Not the giant, supermassive black holes that lurk in the centers of galaxies, or the stellar mass black holes left behind by dying stars. The candidates for dark matter are a different breed entirely. They are called primordial black holes. These are hypothetical black holes that would not have been formed from collapsing stars, but were forged in the chaotic, ultra-dense, and violent moments just a fraction of a second after the Big Bang. In that primordial furnace, tiny fluctuations in density could have been so extreme that some regions of space spontaneously collapsed under their own immense gravity, forming black holes directly. These primordial black holes could come in a vast range of sizes. Some could be as massive as mountains, others as small as a single atom, each one a tiny, perfect point of immense density. And they would be the ultimate dark matter candidate. They are, by their very nature, dark. They emit no light. They are made of ordinary space-time, so they are not some new exotic substance. And they interact with our world in only one way, through their gravity.
They would behave exactly as dark matter is observed to behave. For decades, this idea remained on the fringes of cosmology. But recently, especially after the discovery of gravitational waves from merging black holes, it has seen a quiet resurgence of interest. A universe filled with a swarm of these ancient, invisible objects is a captivating thought. Imagine the night sky not as a mostly empty space with scattered points of light, but as a space teeming with countless invisible points of immense density. Microscopic black pearls scattered on black velvet. They would be drifting silently through the halo of our galaxy, their presence felt only through their collective gravitational pull. Searching for them is incredibly difficult, but we can look for their fleeting gravitational lensing effects. If a primordial black hole were to pass directly in front of a distant star, it would act as a tiny, perfect lens, causing the star to briefly and characteristically brighten. Searches for these micro-lensing events have been conducted for years, and while they have ruled out primordial black holes in certain mass ranges, they have not closed the door entirely. The possibility remains. Perhaps the great mystery of dark matter will be solved not by the discovery of a new particle in a deep underground lab, but by the subtle, ghostly signature of an ancient microscopic black hole as it drifts silently across our line of sight to a distant star. It is a sense of ancient, compact power, of the echoes of creation itself, still floating silently all around us in the dark. The universe was not born into a blaze of glory. After the initial fireball of the Big Bang cooled, the cosmos entered a long, quiet, and profoundly dark period. For hundreds of millions of years, there were no stars, no galaxies, no sources of light at all. The entire universe was filled with a vast, uniform, and transparent fog of hydrogen and helium gas. This era is known, quite poetically, as the Cosmic Dark Ages. The question is, how did it end? How did the very first stars, the pioneers of light, manage to form out of this smooth, featureless fog? The answer is that the fog was not perfectly smooth. And the hero of the story is the silent, patient work of cold dark matter. As we discussed, because cold dark matter was moving slowly, gravity could take hold of it very early on. While the normal matter, the gas, was being pushed around by pressure and radiation, the dark matter was quietly and steadily clumping together, forming the first small gravitational seeds. These were the invisible wells in the cosmic fabric. And into these gravitational wells, the primordial hydrogen and helium gas began to fall. Imagine a vast, cold, still darkness. Then feel, rather than see, a gentle gravitational gathering. A slow, inexorable pull, drawing the thin gas from the voids and into the growing dark matter halos. Over millions of years, the gas within these halos became denser and denser, drawn ever inward by the relentless gravity of the invisible matter. Eventually, in the very centers of these first small halos, the gas became so compressed, so incredibly dense and hot, that a miracle occurred. Nuclear fusion ignited. The first stars were born. These were the stars that brought the cosmic dawn. They were likely immense, hundreds of times the mass of our sun, and they would have burned with a brilliant blue-white light, 1,000,000 times brighter than our own star. They were the ones who ended the cosmic dark ages, bathing the universe in light for the very first time. And they could not have formed without the help of dark matter. The gravity of normal matter alone was not strong enough to overcome the gas pressure and collapse to form a star in that primordial environment. It needed the extra gravitational pull, the deep potential wells provided by the dark matter. Dark matter was the midwife to the first light. It was the dark, silent catalyst that allowed the universe to finally shine. As you feel yourself drifting towards sleep, picture that long, silent darkness. Feel the patient gravitational gathering, the slow compression, and then visualize that first single point of warmth, that first star igniting in the vast emptiness. Then another, and another, and another. A slow, gentle sunrise spreading across the entire cosmos,
all of it made possible by the quiet, foundational work of the universe's invisible architect. Now, let us bring this cosmic story all the way home, to our own front door, to the beautiful spiral galaxy we inhabit, the Milky Way. All of the phenomena we have discussed, the galactic glue, the cosmic web, the seeds of the first stars, are not just things that happen out there in other distant galaxies. They are happening right here, right now. We are living inside the story.
Our Milky Way galaxy, that beautiful swirling disk of 100 billion stars that we see as a faint milky band across the night sky, is just the visible component of a much, much larger structure. We are embedded in a gigantic, roughly spherical halo of dark matter. This halo is immense. The visible disk of our galaxy stretches about 100,000 light-years across. But the dark matter halo extends for at least 1 million light-years in every direction, perhaps even further. It is a vast, invisible cloud, and the starry galaxy we call home is like a small, glittering jewel suspended in its very center. And this halo is not just large, it is massive. It contains at least 10 times more mass than all of the stars, gas, and dust in our galaxy combined. We are utterly dominated by its gravitational presence. This means that as you lie here now, you are inside it. We all are. Our entire solar system, our sun, the earth, this very room, are all moving through this vast, invisible cloud of dark matter. We are like fish swimming in a deep ocean, completely unaware of the water all around us until we stop and think about it. And our journey through this ocean is not a slow one. The entire solar system is orbiting the center of the Milky Way at a speed of about 500,000 miles per hour. And as we race along, we are constantly moving through the dark matter halo. So there is a wind of dark matter particles constantly blowing through the Earth, through you. This is what those deep underground experiments are trying to detect. They are trying to feel the faint, imperceptible breeze of this cosmic wind. There is a profound sense of comfort in this realization, a feeling of being held, of being enveloped by the cosmos. We are not just isolated on a small, fragile planet, adrift in an empty void. We are part of a grand, invisible structure. We are held in place by its gentle, persistent gravity. Our cosmic home is safe, stable, and secure, all thanks to this vast, soft, invisible sphere that cradles us in its unseen embrace. The universe is a story of change, of evolution over immense timescales. Stars are born, they shine, and they eventually die. Galaxies collide and merge. Nothing is truly permanent. And so it is fair to ask, is dark matter stable forever? Does this silent, invisible substance last for eternity? The standard model of cosmology assumes that it does. It assumes the dark matter particle is perfectly stable and will never decay. But some theories, some whispers from the edges of physics, suggest a different possibility. They propose the idea of decaying dark matter. In these models, the dark matter particle is not perfectly stable. It is incredibly long-lived, far, far more stable than any normal particle, but it has a finite lifespan. Over trillions upon trillions of years, an almost unimaginable timescale, a dark matter particle might spontaneously decay, transforming into other, more familiar particles, perhaps a neutrino and an antineutrino, or a faint photon of light. This would be a form of cosmic radioactivity, but happening on a timescale that makes the decay of uranium seem like an instantaneous flash. Why would scientists consider this idea? It's because while the cold dark matter model is incredibly successful on large scales, there are some small, subtle discrepancies between its predictions and our observations of the very centers of small galaxies. A slowly decaying dark matter could potentially resolve some of these tensions, creating a slightly better fit with the data. If this were true, it would mean that the universe's dark matter is very slowly, almost imperceptibly, evaporating. It would mean that the cosmic web itself is slowly dissolving, its mass bleeding away into faint radiation over timescales that dwarf the current age of the universe. We could never hope to see a single particle decay, but we might be able to detect the cumulative effect of countless decays happening all across the cosmos. This slow decay would produce a faint, diffuse glow of radiation from all directions, and telescopes are searching for just such a faint, unexplained background signal. Imagine a sound that is so low, so deep, and so slow that you can't possibly hear it as a distinct note, but you can feel it. A subtle, persistent vibration, a background hum to reality. This is what decaying dark matter would be like. The universe would be filled with a faint, background hum from the slow, patient, and final decay of its own invisible matter. It is a reminder that even the most seemingly permanent structures of the cosmos are in a state of slow, graceful, and peaceful transformation. And so, we arrive at the edge of our knowledge. We have traveled through the invisible architecture of the cosmos. We have weighed the evidence, explored the theories, and journeyed to the deepest minds and the farthest reaches of space. And after all of this, we are left with the most profound and beautiful fact of all. The simple truth is, we do not know what dark matter is. It remains one of the greatest, most compelling, and most fundamental unsolved mysteries in all of science. It is a shadow that stretches across our entire understanding of the universe. And this is not a failure. It is not a sign of our ignorance, but rather a testament to the grandness of the cosmos and the boundless potential for future discovery. This mystery is an invitation. It is the universe, in its deep and subtle way, challenging us to look deeper, to think harder, to be more creative, and to build more sensitive experiments. It is a promise that there are still fundamental new discoveries to be made about the nature of reality. It tells us that we have only just begun to map the territory of what is. Our most powerful theories, the Standard Model of particle physics and Einstein's general relativity, are like two magnificent, brightly lit islands of understanding in a vast, dark, unexplored ocean. And dark matter is a shape, moving in that deep water. We can see its effects, we can chart its course, but we do not yet know its true form. To be a scientist, to be a human being, is to learn to be comfortable with this feeling. The feeling of standing at the edge of a calm, dark ocean, under a sky full of stars, knowing that incredible wonders lie just beneath the surface, waiting to be discovered. This beautiful unknown is what drives us. It fuels our curiosity. It inspires our art. It is the quiet excitement for the discoveries that our children and our children's children will one day make. And so, as we conclude our journey through the hidden facts of dark matter, let us not be left with a sense of an unanswered question, but with a sense of peaceful, profound wonder at the magnificent scale of the mystery itself. Now, let the facts and figures, the theories and discoveries begin to gently dissolve. Let the vastness of the cosmos recede, like a quiet tide going out. Your journey tonight has been a long one, across billions of light years and billions of years of cosmic history. But now it is time to come home, to the gentle, peaceful space of your own deep rest. Allow the cosmic wonders to become a soft, shimmering background, a beautiful tapestry upon which you can drift into sleep. You are held in the unseen embrace of the universe, the same gentle gravity that holds the stars in their courses. You are part of the hidden scaffold, a precious, luminous point in the vast, interconnected web of reality. The great and beautiful mystery of the cosmos is not outside of you, but within you, and you do not need to solve it. You only need to rest in it. Feel your awareness returning now to the simple, gentle rhythm of your own breath. A slow, easy inhale and a long, soft, complete exhale. With each breath out, release a little more. Release the need to know. Release the need to understand. Just be. Drift now. Let go. Allow the soft darkness behind your eyes to merge with the deep, quiet darkness of space. You are safe. You are held. You are at peace. The whispers from the Milky Way are fading now, dissolving into a profound and healing silence. There is nothing left to do, nothing left to think, only to rest, to drift, to dissolve into deep, peaceful, restorative sleep. Sleep now, friend, sleep. And so, our journey through the cosmic shadows comes to a gentle close. We have wandered the vast, invisible cathedral of the universe, feeling the presence of its silent architect. We have felt the cosmic glue that holds our galaxy together, a firm but gentle embrace, preventing the stars from scattering into the lonely void. We have traced the threads of the cosmic web, the delicate, unseen scaffolding upon which all the light and life of the cosmos is built. We have traveled deep underground, into the quietest places on Earth, to listen for a single faint whisper from a passing cosmic ghost. And we have stood at the edge of a great and beautiful ocean of the unknown, not with fear, but with a sense of profound and peaceful wonder. Let these cosmic thoughts now begin to soften, to recede, like the faint light of a distant galaxy sinking below the horizon. Let the immense scales of space and time dissolve into a feeling of deep, quiet, and present calm. The universe has shared some of its deepest secrets with you tonight. The secret that you are held by an unseen embrace. The secret that you are part of a structure far grander than you can see. And the beautiful secret that mystery is not a void, but an invitation to dream. And now, it is time to let it all go. Gently bring your awareness back from the farthest reaches of space, back from the swirling star fields and the silent invisible halos. Bring your awareness home. Home to the quiet sanctuary of your room. Home to the gentle weight of your body, resting comfortably, feeling heavy and relaxed. Home to the simple, peaceful rhythm of your own breath. There is nothing more to learn tonight, nothing more to understand. The journey is complete. All that remains is rest. Feel the gentle rise and fall of your chest, a slow, steady, peaceful rhythm. Each breath in is calm. Each breath out is a release. Breathing in, a sense of quiet. Breathing out, letting go completely. The wonders of the cosmos can now dissolve into the peace of this moment. The invisible matter, the bending light, the cosmic web, let them all merge into a single, simple feeling of profound relaxation. You are safe. You are held. You are drifting now on a calm, quiet, endless river. Let the current carry you. Release all effort. Release all thought. Dissolve into the darkness behind your eyes. It is a soft, welcoming darkness, a healing darkness. Let it envelop you like a warm, soft blanket. Every part of your body is heavy, calm, and deeply relaxed. Every part of your mind is quiet, still, and at peace. There is nothing left to do now, nothing at all, but to drift, to float, to release, and to allow yourself the profound gift of deep, restorative sleep. Drift now, dissolve into peace. The whispers from the Milky Way have faded into silence, and now you can rest. Sleep now, friend, sleep.